Okay. Hello, everyone, and thanks for coming. And I'm so glad that I can share a summary of my dissertation today, which has been supervised by Professor Khattak. So the title of the dissertation is a multi-level study of driving behavior and system performance, harnessing large-scale naturalistic driving data. I start with the introduction. In the field of transportation, there are different measures of performance, including constant repair and maintenance, efficient and reliable mobility, economic competitiveness, and improving safety and conserving natural resources. In this dissertation, we focused on the last two measures, and our whole goal is reducing crashes and reducing emissions. Why these measures are important? Well, in 2019, we know that about 30,000 fatalities happened in the US, which costed about 800 billions. And we know that regarding the fuel economy emissions in 2019, about 1,000 million metric tons of carbon dioxide emissions were from vehicles, which made up about 22% of the energy-related emissions. So these measures are so important. Numan and Iman talked about the driving behavior factors and how they are important. I want to add that also driving behavior has an important impact on carbon dioxide emission that I'm going to explain that in the next slide. So we know that driving behavior factors are so important, but collecting the driving behavior factors is a real challenge because they are usually costly to collect, hard to quantify, and also we always should deal with privacy issues. However, nowadays with the emergence of connected and automated vehicles and onboard sensors, we have unprecedented access to the information of the drivers. And we can use advanced statistical models and machine learning methods in order to extract useful information from the data. So here are the questions that we are going to answer in this dissertation. How to harness the new data to improve transportation system performance. How to incorporate driving behavior factors in transportation safety. How can we integrate the new data with conventional data, like crash data, to study multi-level driving behavior? Okay, I start with the first chapter, which is entitled Classifying the Travelers' Driving Style Using Basic Safety Messages Generated by Connected Vehicles. A version of this chapter was published in Transportation Part C. And, okay. So the overall goal of this study was developing a framework to harness basic safety messages generated by connected vehicles to classify driving style in different spatial contexts. So we used the SPMD program data, the connected vehicle data. It contains more than 2,800 connected vehicles, more than 2 billion of basic safety messages. And the study area is limited to Ann Arbor, Michigan. We also use zoning map data in order to identify roadway types in different neighborhoods. We found that driving style not only can vary among drivers, but also over time. Also, we found that thresholds for aggressive driving vary across different roadway types. Also, we found that the proportion of aggressive driving is higher on commercial streets compared to residential streets and highways. This paper contributed to the field by studying driving style under naturalistic driving condition, quantifying variations in instantaneous driving behavior using volatility measures. And also we propose an approach for calculating driving score as a measure of driving performance. Here is the conceptual framework of the study. We use zoning map data in order to extract roadways in different neighborhoods using land use. And after extracting the BSMs for randomly selected segments on these neighborhoods, we calculated the volatility measures. And then using a clustering approach, we clustered drivers in different neighborhoods. And finally, we calculated the driving score for drivers. We classified driving events into 3 clusters in each roadway tab. And this table shows the scale mean values of classification features for highways, commercial streets, and residential streets. Generally, there is a trend in a way that cluster 1, 2, 3 have the highest driving volatility measures respectively. And it can be depicted more clearly in a radar chart. As you can see, the larger the blue region is, the higher the value of the classification features or volatility measures. So it is logical to allocate the large, medium, and small regions to aggressive, normal, and calm driving style, respectively. Here are the classification results for the different neighborhoods. This table shows the results for that, and you can see that, for example, in highways, about 11% of the events were classified as aggressive driving, while this percentage for commercial estates was about 24%, which is consistent with the complex and various environment in this neighborhood. We also use a PCA in order to show these clusters in a 2-dimensional environment. And as you can see, the cluster for the calm driving is more impact than the other classes, showing that the majority of the clusters are classified as calm drivers. Finally, we proposed a driving score, which evaluates the driving performance of the drivers. And the driving score ranges between 1 and 3. Driving score of 3 represents calm, and driving score of 1 represents aggressive driving. And as you can see, this figure shows the distribution of the driving style in different neighborhoods. Okay. In chapter 2, the chapter 2 is entitled Analyzing the Impact of Instantaneous Driving in Work Zones and Curves and Emission and Fuel Efficiency using Naturalistic Driving Data. This paper is going to be presented in the next review. So the overall goal of this study was analyzing emissions and fuel consumption within work zones and curves using NDS data. We used the SHRP2 naturalistic driving data, one of the most comprehensive naturalistic driving study in the US. Newman talked about this data, so I don't go to the detail, but we found that an average increase of 12% and 15% in emissions in work zones and curves compared to the other locations. Also, we found that aggressive driving on curves decreases the fuel economy by 23% and increases emissions by 18%. Also, we found that aggressive driving in work zones resulted in an average 60% decrease in fuel economy and about 40% increase in emissions. The contribution of a study was evaluating the effect of driving style in work zones and curves on emissions and fuel consumption. Also, we evaluated the effect of traffic flow, roadway type, driving style on emission and fuel consumption using real world condition data. This figure shows the conceptual framework of the study. We used the SHRP data. After the pre-processing, we calculated the driving volatility, and after clustering the drivers in different locations, we used autonomy software simulation. I talked about that in order to simulate fuel consumption and emissions. So the autonomy modeling uses the real commands in order to simulate fuel consumption and emissions based on the real world conditions. So that's why it is more accurate than the other models. For example, let's say there is a desired speed. So the autonomy model estimates the real torque needed for achieving the speed. Then it simulates the power controller in order to send real commands to other components, such as engine, clutch displacement, gear transmission in order to get to that speed. So it considers the physics of the vehicle in order to simulate the fuel consumption. And that's why it is more accurate than the conventional equations. We followed the same procedure as discussed in the last chapter in order to classify drivers in different locations, work zones, curves, and freeways and arterials. Classify drivers into 3 clusters. And you can see the classification results. For example, in work zones, we have 12% of the drivers classified as the aggressive drivers, while this percentage on curves is even higher, 15%. Then on the freeways and arterials, you can see that about 17% of the drivers were classified as aggressive driver, and this percentage for arterials is about 25%. Here are the results for the autonomy software modeling. The y-axis shows the gallons per mile, which often called MPG on vehicles. The higher the MPG, the lower fuel consumption and higher fuel economy. And on the x-axis, we have driving style in different locations. We found that on average, aggressive driving decreases fuel economy by 19 and 14 and 19 and 40% for within curves and work zones, as opposed to calm driving. And this figure shows the fuel economy estimates for freeways and arterials. Based on our result, aggressive driving resulted in 50% and 28% decrease in fuel economy on freeways and arterials. Also, these are the emission estimates from the autonomy model. On the y-axis, we have the kilogram of greenhouse gases per kilometer, and you can see that as driving transitions from calm to aggressive behavior, emissions increases by 25% and 42% within curves and work zone respectively. Also, on freeways and arterials, our results show that higher emissions rates are about 15% and 10% for aggressive driving on freeways and arterials. Okay, so in chapter 3, the chapter 3 is entitled Understanding How Relationships Between Crash Frequency and Correlates Vary for Multi-Lane Rural Highways. This chapter was published in the Journal of Accident Analysis and Prevention. So the overall goal of this paper was the localization of SPFs, which are used in the HSM by taking into account spatial-temporal instability in road crashes using geographically and temporally weighted regression models. We use the crash data for Tennessee for multi-lane highways belonging to more than 900 multi-lane highway segments, also the coordination of the segments. Our results shows that the GTWM model remarkably outperformed the traditional regression models, and most parameter estimates vary substantially across space and time. Also, our results weaken the idea of transferring default SPFs to other states. This paper contributes to the field by demonstrating the application of GTWR models in traffic safety. Also, it incorporates spatial temporal heterogeneity of road crashes and investigates the variation of safety performance function parameters across space and time. Here is the conceptual framework of the study. We had the data, including basic factors such as ADT and segment length, crash data, and also additional factors such as geometric features and traffic features. We had two major groups of models. The first group of model is the regular global models, conventional models using the HSM, using the negative binomial models. In these models, we use the whole sample in order to estimate just one model, single model, and each sample has equal weight. So associations are stationary and are spatio-temporally independent. In the GTWR model or local model, however, we use subsamples to estimate model for each location. And in each subsample, we consider those observations that are spatio-temporally adjacent to each other. So therefore, associations can be spatio-temporally dependent in these models and can improve the fit of the model. Here you can see the result of global and local models with just key variables or base models that just considers the ADT and segment lengths. As expected, these variables are significant and positively associated in the model, in both models. And based on the AIC and McFadden R-squared, you can see that the local model has a better performance than the global model. In this model, we considered additional variables beside the ADT and segment length, variables such as speed limit, lane width, median type, land use. And you can see that AIC decreases, meaning that it outperforms the base SPF. Finally, this model shows our final model, which is a local model considering all the variables. And you can see that the AIC improves significantly, showing that considering a spatial-temporal heterogeneity can improve the performance of the model. And these are the results of non-stationary tests. You can see that the majority of the variables pass the test, showing that they vary significantly across space and time. Here you can see the spatial variation of the local parameter estimates in Tennessee. This figure shows that the spatial variation of local parameter estimates at country level, and you can see that parameter estimates can be partially stationary in some regions, but they are variable across jurisdictions. For example, variable ADT has a relatively stable parameter in West Tennessee, but going from the west of the Tennessee to the east, the effect of the variable increases significantly. And here you can see the temporal variation of the local parameters. And for two key variables, ADT and segment lengths between 2013 and 2017. And as it is depicted in the figure, although there was a positive association between these two variables and number of crashes, the spatial pattern varies over time. So overall, we can conclude that spatial temporal variation of contributing factors in this study shows that considering variable estimates to be constant over time and space is very simplistic and biased. So we can use GTWR models and local models to address this issue. Okay. In chapter 4, it is entitled Incorporating Driving Volatility Measures in the Development of Safety Performance Functions for Intersections. And this chapter is also going to be presented in the next TRB. The overall goal of this study was to incorporate driving volatility measures in the development of SPFs for four-leg signalized intersections. We use the same data as we used in chapter 1, the SPMD data. Also, we integrated the connected vehicle data with the conventional crash data. About the contribution of the paper, it provides a framework to harness larger scale CAV data to incorporate driving behavior factors in intersection SPFs. Also, we are applying a Bayesian hierarchical model to account for the spatial correlation between the adjacent intersection, the network that I explained about the model. Here you can see the conceptual framework of the study. On one hand, we have the connected vehicle data. On the other hand, we have the conventional crash data. We kind of integrate these two databases, and after that, we develop three different models, including conventional negative binomial, random effect negative binomial, and Bayesian hierarchical negative binomial. So about the Bayesian hierarchical modeling, the advantage of this model is that they not only take into account this spatial correlation between the adjacent intersections, but they can capture unobserved heterogeneity at a two-level hierarchy, with one level at corridor level and level 2 at the intersection level. And we do that by considering the adjacency matrix of the intersection. We consider the different measures for model comparison. We have DIC, deviance information criteria, which is a summation of the posterior mean of deviance, effective number of parameters, which is kind of the trade-off between goodness of fit and the complexity of the model. We expect smaller values for a better model. Also, we have log pseudo marginal likelihood, which is based on leave one out cross-validation. And it shows the predictive performance of the model, and we expect larger values for this measure. Also, we have mean absolute deviation and mean square errors that we expect smaller values in order to improve the predictive performance of the model. Here you can see the estimation results of the model without any volatility. So in this step, we didn't consider any volatility in order to have a logical comparison. Here you can see that as expected, ADT of the major and the minor approaches are associated with the number of crashes at intersections. And then in the second step, we added the volatility measures to see how it improved the model. We had three volatility measures, coefficient of variation of speed, deceleration, and acceleration significant in the model, and they are positively associated with the number of crashes. And in the third step, we also consider some additional variables, such as right turn length, left turn signal phase, if it's protected or not, right turn on red, red light camera, and also presence of the school in the area. So here is this table shows the performance comparison of these models. You can see that based on DIC measure, we can say that the first of all, adding volatility measures improves the goodness of fit of the model significantly. Secondly, taking into account the spatial correlation between the intersections can improve the goodness of fit substantially. And we have similar trend in LPML and MAD and MSE, showing that incorporating the volatility measures as surrogate measures of safety is very promising. And also the best approach is to consider hierarchical Bayesian modeling in order to capture the spatial correlation between the intersections. Okay, chapter 5 is entitled How Are Physical Conditions and Driving Errors of Commercial Large Truck Drivers Associated with Injury Severity in Fixed Object Collisions? This paper is under review in the Journal of Transportation Safety and Security. So the overall goal of this study was to investigate the effect of large truck drivers' physical conditions and driving errors on the severity of fixed object crashes involving large trucks. We use the crash data, 5 years of crash data between 2013 to 2017 for North Carolina. And we found that having a medical condition, having illness, falling asleep, impaired driving, and fatigue driving have a strong association with the severity of the crashes. Also, we found that speeding, oversteering, and aggressive driving increases the probability of fatal injury crashes. The contribution of a study is exploring the physical condition and driving errors of large truck drivers, and also investigating the pure effect of large truck drivers' behavior, because in this study, we are considering only single vehicle crashes. So the large truck drivers are the only one involved in the crash. Also, we are applying a random parameter model in order to account for unobserved heterogeneity. Here is the conceptual framework of the study. We have the HSIS crash data, including the accident file, vehicle file, and roadway file. And after merging these databases, we had data cleaning, crash data. We had the crash data in a crash level. Then we had a subset of crashes and track involved crashes. And also, finally, we had a subset of fixed object crashes involving large trucks. And we had the model estimation. So there are two major groups of variables: physical condition variables and driving error variables, and we are controlling them by the roadway features and driver features. Here you can see the modeling results of our model, both random parameter model and fixed parameter model. As you can see, variables, road alignment, ADT, and speed limit were random in our random parameter model. And based on the goodness of fit measures, you can see that the random parameter model outperforms the fixed parameter model. Variables about the physical condition of the large truck drivers, variables, illness, fatigue, falling asleep, impaired driving, and medical condition were significant in the model. And about the driving errors, disregarding sign and signals, like speeding, improper lane change, wrong way driving, oversteering, aggressive driving, and operating with defective equipment were significant in the model. In order to better interpret the coefficients, we provided the marginal effects. Based on the marginal effects results, we can see that the large truck drivers with a medical condition are about 13% more likely to be involved in fatal or severe crashes. Also, our model shows that drivers who had an illness, for example, are 5% more likely to be involved in fatal and severe injury crashes. Also, speeding is another important factor. Based on the results, speeding increases the likelihood of the fatal and severe injury crashes by about 2%. Here are the implications of this study. Our results underscore the periodic medical monitoring of the truck drivers. Currently, truck drivers should take the DOT's medical exam every 24 months, but shorter intervals can help for a better, monitoring the drivers. Also, regulations can be revised for shorter hours of service to prevent the fatigue driving of the drivers. Using a biometric driving monitoring system to detect the sign of drowsy driving is another option. Also, new technologies such as connected trucks and truck platooning can be helpful in order to detect traffic violation and speeding. Okay, with that, I go to the conclusion. Here are the contribution of the study. We developed a methodological framework to harness large scale naturalistic data to evaluate transportation system performance. We evaluated the system performance in correlation with driving behavior at different levels, driver level, location level, roadway level, and network level. We used the concept of driving volatility. We had some new applications for that. We use driving volatility in order to classify drivers in different roadways. Also, we use that for analysis of emissions and fuel consumption. Also, we consider the deriving volatility measure as a measure of deriving behavior in development of the SPFs. Also, this study links several data sources, including macroscopic imaging big data and conventional transportation data. And also we applied rigorous statistical models such as GTWR and Bayesian hierarchical modeling to capture temporal and spatial unobserved heterogeneity in safety models. Okay, I'm finished. And if you have any question. Questions. Okay. Okay. So both.
Can you repeat the question?
Yeah, Yang Song asked that you wanted to know what is the difference between these two models. Okay, so technically, random parameter model considers the heterogeneity between the observations, but it's not necessarily spatial heterogeneity. So in this case, for example, for random parameter model, it considers like a normal distribution for the coefficients of the variables, but they are not necessarily a spatial correlation between the observations. So this is the difference between these two models. So it depends in the case. If you have a spatial correlation between your observation, of course, using a heterogeneity model with, using a spatial correlation is better. In the case of our study, you always have spatial correlation between adjacent intersections. So let's say there are two, adjacent intersections, and you always see that, the crash numbers are kind of the same because they have the same traffic characteristics and, segment characteristics. So in that case, if you see that there is a spatial correlation, it's better to, consider those models. Which one? Oh. Chapter 4 or 3? Oh, yeah. Okay, which one? Oh, this one. Okay.
Can you?
Oh, sorry. Okay. You're talking about those counties that are gray. We didn't have data for that. Of course. Yeah, I see what you mean. Yeah, of course. If you have the whole sample, it's perfect. But the thing is that collecting data for, such, segments, it's very time consuming. And let's say there is like 2,000 segments for multi-lane highways. You cannot, collect data for the whole sample. So you always end up with a random sample, let's say 400, 500 samples, and you do that. So in this case, there are some counties that you don't have any multi-lane highways in that county. So sometimes you don't have any data for that, and sometimes you're not able to collect the whole sample for that, study. So Yeah. You're welcome.
Did you just consider highway crashes in this paper?
Highway
Crashes in this paper.
grasses,
Highway accidents.
accidents. Yeah, highway accidents.
Do you think the result is replicable in urban crashes in cities?
You mean what result? You mean the
Results.
yeah, you can do that for and you know other type of the roadways. Yeah, of course.
Do you expect to find similar results? Or
Yeah, I expect that you can find some spatial temporal correlation between the segments. Yeah, of course.
okay, thank you. Let's give another hand.
You're welcome.
So moving on, since we are pressed for time, thank you. Okay, so Aboubakr is joined us also in August 2018, and he is pursuing his PhD here, has a bachelor's degree from University of Khartoum in Sudan, and also master's degree from University of Tennessee at Chattanooga. He's worked professionally in public transit, and we are glad that he decided to come back to academia and is pursuing his PhD. His research focus is on quantifying the impacts of emerging factors like shared e-scooters and transit ridership. And he's interested in transit planning and operations and transit fare policy and technology. So with that, Aboubakr, thank you. And the floor is yours.
Thank you, Dr. Khatak, for the introduction. Today I will be talking about the impact of shared scooters on bus ridership, and I will note that this will be a chapter of my dissertation. I will not be presenting the whole dissertation, as the other chapters are still in progress. So the results of this study was recently published in Transportation Research Part A. And before starting, I would like to acknowledge my co-authors, Wesley Darling, Dr. Candice Breakwood, Dr. Harry Watkins, and Dr. Ed Hart, and then the Transit Research Cooperative for funding this study. So the outline of today's presentation, I will give a brief background, an objective and a research question, discuss the data and method, and then the methods that we used to assign the shared scooter trip to transit routes, then results and discussions and conclusions, and I will discuss also some areas for future research. So shared scooters are just everywhere. Like you can just see them in every street, in every corner. They're increasing in popularity in the United States before COVID-19. In 2018, they were about 38.5 million trips, and then this number in 2019 went to 88.5 million shared scooter trips. In this time, the transit agencies in the United States were concerned about ridership declines. And then this timing raises a question like, do shared scooters contribute to transit ridership declines, which will be the focus of this analysis. So how shared scooters could impact transit? There are different possibilities. First, they could complement transit, as they could serve as first mile, last mile, and then in this case, they will increase the accessibility of transit, and they will increase transit range. Another possibility, they could be competing with transit, as they could replace their transit trips with scooter trips. And this case will have negative impact on transit. And the third one, they could have no impact on transit. For example, they could be used for other purposes, like recreation, or they could be used to replace other modes like walking or car trips or Uber or Lyft. So then the prior findings about shared scooters' impact on transit showed mixed findings that I will be showing. So there are a group of studies that conducted user surveys, and they asked users like, do you use shared scooters to connect to transit or to replace to transit? And as we can see in the same cities, we see different people using them for different reasons. While we can see here this higher percentage of riders said that they are using them to connect to transit, these findings are not conclusive because surveys, this survey did not consider the frequency of connecting or the frequency of replacing. So it might we don't know the net impact. Also, surveys, they have like some biases, as we all know, like the social desirability bias or the non-respondent bias. So, another group of studies, they tried to use empirical methods. Like one study in Indianapolis, they said like one third of the shared e-scooter trips, they could complement transit, while another said they could compete with the bus. And then another study in Austin, they said like scooters and transit are positively correlated in the downtown, but they are negatively correlated outside the city center or the downtown. But then these studies, they did not quantify the net impact, which will be the focus of this study as we aim to quantify the net impact of shared e-scooters on bus ridership in Louisville, Kentucky. And I will be discussing why we chose Louisville, Kentucky for this study. In this study, we try to answer 3 research questions. First, do shared e-scooter increase ridership on express bus route? And then the second question is, do shared e-scooter increase ridership on local bus routes? And the last question is, do shared e-scooter decrease ridership on local bus routes? And I would like to note that we explore the local bus routes and the express bus route separately, as they have different trip characteristics, and the shared e-scooter impact on them might be different. And also, we did not explore the possibility that shared e-scooter could decrease ridership on express bus route, as the express bus trips typically very long, and they have one of the trip ends typically occur outside the shared e-scooter service area, which typically around downtown and urban areas. So why we chose Louisville for this analysis? First, there were limited changes to the transit service in Louisville during the period of the analysis. So we could explore the impact without worrying about other changes in the transit system. And the second reason is the popularity of shared e-scooters in Louisville compared to transit. And then third and most important is the availability of shared e-scooter trip data freely accessible to the public, which is not something that all cities have. So in this study, we use a fixed effect regression, and our dependent variable was the unlinked passenger trips for bus routes for each day. And the explanatory variables were shared e-scooter trips counts, and then vehicle revenue hours, for example, and some other variables that affect transit ridership. And we use two-way fixed effect. We use entity fixed effect and time fixed effect to control for unobserved variables. This is just a quick look for this table shows that different data sources that we used. We used the linked passenger trips, as I said, the vehicle revenue hours, the shared e-scooter trips, plus population, employment, demographics, weather. And the period of the analysis goes from February 2016 to December 2019, which has periods before and after the shared e-scooter launch in August 2018. So to evaluate our research questions, we defined different variables based on the shared e-scooter locations compared to transit routes. And we defined for each research question, we defined variable. For this research question too, we defined 2 variables because there's 2 possibilities, and I will be discussing this in each of these variables in detail, like the shared e-scooter complement count, shared e-scooter first mile count, and then last mile and substitute. So the first variable we defined is shared e-scooter complement trip count, and this variable we defined only for the express bus route. And then in this figure, you can see that, I don't know if you can see or for this variable, we counted the number of shared e-scooter trips that started within the bus catchment area in the morning or ended within the bus route catchment area in the evening. And the assumption for this variable that commuters could ride shared e-scooter from the bus stop in the downtown to their workplace in the morning, and in the evening they could do the reverse, and they could ride shared e-scooter from the workplace to the bus stop in the evening. And then for the local routes, we defined the shared e-scooter first mile trip count, and this variable counts the number of shared e-scooters that ended within the bus route catchment area. And the assumption in this case, users could ride shared e-scooter from their trip start point to the local bus stop. And similarly, we defined the shared e-scooter last mile trip connector trip count, which is violating the other assumption. It's that shared e-scooter is the last mile connector. People will use it from the bus to their trip endpoint. And then the last variable we defined is the shared e-scooter substitute count. And in this variable, we counted the trips that have both origin and destination within the bus route catchment area. And the assumption here is that riders could use shared e-scooter to replace bus trips. And in this case, the shared e-scooter will start and end both in near the transit routes. So based on these different trip variables that we defined and the other transit variables, we estimated different fixed effect regression models. And here I will be showing them in this table. So this table shows the results of evaluating research question 1 and 2 that do shared e-scooter increase ridership on local and bus and express bus route. And here this table shows the weekday model, and in the weekday model is from Tuesday to Friday. And the reason to exclude Monday is Monday ridership data was aggregated with the weekend, so we excluded that. So we don't. We want to focus more on the weekday analysis. And as you can see here, the vehicle revenue hour is a highly significant predictor of bus ridership as expected, as this is one of the variables that the main determinant of transit ridership. And also, you can see here the shared e-scooter trip complement count is a significant predictor for express bus route ridership, which say that it has a small positive impact on express bus ridership. But on the other side, we see that both the first mile and the last mile for the local bus route are not significant predictors. Then we can see that they don't have a significant impact on bus ridership. So as I said, the weekday, the Monday data was not available. So we estimated weekday model, and then we ran also weekly models and monthly model to evaluate the robustness of our analysis. And we see that the weekly and the monthly model were both consistent with the weekday model. In the monthly model, we also controlled for other variables like population, proportion female, proportion white, and proportion of seniors and weather, and all of these variables had the expected impact and as prior studies showed. This table shows the results of the evaluating research question 1 and 3 that do shared e-scooter increase ridership on express bus route and decrease ridership on local bus route. I will be showing just the weekday model, but we run also weekly and monthly model, which also were consistent with this. As you can see again, the vehicle revenue hours is a significant predictor, and the trip complement count again is positive and significant, but the substitute count is not significant. So based on these results, we can see that the shared e-scooters don't have significant impact on local bus ridership in Louisville. And some of the possible reasons for this result is the different trip purposes for transit and shared e-scooter in Louisville. For example, transit in Louisville basically used for work and school, while shared e-scooters are likely used for recreation. Another one could be the different demographic group of demographics for riders. For example, in Louisville, transit riders are typically African Americans and have lower household income, while different surveys showed that shared scooter users are likely to be white and have higher household income, so the different groups of riders may limit the impact of shared e-scooters on bus ridership. So for the express bus route, the models also suggest that the shared e-scooters could complement express bus route. And then this finding should encourage transit agencies and shared e-scooter operators to explore ways to promote the usage of these two modes. For example, they could offer integrated trip planning applications that you can plan your trip using transit and scooter together, or you can also, they offer fare payment integration or some discounts for using these two models. However, I will just like say this finding should be interpreted with caution, since many of the transit express routes they terminate in the same geographic area in downtown, which resulted in similar counts of shared e-scooter, which is limitation of our study. And to summarize our findings, first, shared e-scooter could possibly complement express bus route as they serve as first mile, last mile. And then shared e-scooters, they neither compete or complement local bus routes. And then the main finding that shared e-scooter is not one of the primary cause of bus ridership decline in Louisville. And then another finding of this study, there are some areas for future research. For example, there could be a survey for express bus route riders to explore how to better serve them with transit and shared e-scooters. And then, as Louisville is one city with one city that does not represent all cities in the United States, other studies should look at different cities with different transit systems. Also, as Louisville has only bus service, as future studies could also explore the impact of shared e-scooters on rail ridership. Thank you, and I'll be happy to take any questions.
Hey, Aboubakr, you here? Can you hear me?
Thank you for the question. So in this study, we didn't consider this for two reasons. So the first one, like first, this thing was everything in this analysis was prior to COVID and everything was normal. So we didn't consider that, but I expect after COVID, there will be a different impact because different travel behavior will emerge after COVID. And the second thing is the transit ridership generates aggregated at the day level. So the bus will be, the data will be counted by the end of the day. So you cannot know like how many people rode for how long. Like we just know how many people rode, but we don't have data on the trip length. So which is a limitation of the transit data generally. Yeah, but that's possible, a possibility after COVID-19. Yeah. So we took the accumulative snowfall and the accumulative rainfall for the month. Yes, for our rainfall. If not the scooters, what might cause the decline in transit ridership in Louisville? Okay, thank you for the question. So there are different factors. One of them is, of course, the gas price. Like gas prices were declining, so when the gas price is declining, people will generally travel more by car. The other one is the transit service itself, it's reducing. So the transit is not serving many people as it used to be. And then another one is the transit fares. Transit fares are are increasing generally. So people again are reducing their transit services. And there are several other factors. One of them is all, of course, is Uber, as people are using Uber more frequently. Okay. Yeah, so these modes were there before the shared scooters, and shared scooters were just the recent thing. And the other thing is in the model we included like the day fixed effect or the time fixed effect. So the time fixed effect will control for other unobserved variables that we have in the model. For example, if in a specific day people are taking bikes more or they are using cars more, that day time fixed effect will observe that impact. Yeah. Normal distribution.
So can you explain a little bit about the model and your dependent variable and when this mode was introduced exactly, and then how much of that mode was introduced, and how much of it was available and how much of it was used? So is that captured somewhere in the model?
So
Maybe I missed it.
okay. So here in the model,
So this is time series, right?
This is panel data.
Yeah.
We have yes, different bus routes and then many days. So in the first period of the analysis, so in the X variable here, we have variables that count the number of shared e-scooters. So in the beginning, before the shared e-scooter start, this variable will be 0 for everything. But then after the introduction of the shared e-scooters, for each bus route, it will have a different count on that specific day.
So how many bus routes do you have?
About 45.
Okay. So, and for each one, you will see over time that
Yes.
there's more and more.
More shared e-scooters.
But not the supply, just the use.
Yes, in this analysis, we are just looking at the demand side. Yes.
Okay. And then this model that you're estimating, like you chose fixed effect.
Yes.
So what about random effect?
So with fixed effect for 2 reasons. The fixed effect will allow each bus route to have its specific intercept. So we'll say like the behavior of the people on it. So the random effect will not capture that. So that's the first one. And the second one is the random effect to be consistent. It will require more strong assumptions. So we wanted to relax that by using the fixed effect regression. So the strong assumption will be all the unobserved, they don't vary by route. Like for example, in each part of the city, all the residents will have similar attitude toward transit and all other, which the fixed effect will able us to capture that.
But not ideally, but
yeah.
But okay, yeah. But as you were saying, and as Yan Song was saying also, I mean, if you can get those explicitly, those variables that are kind of, you're saying are part of this noise or error term, as many as you can get into it. Now I know you have data limitations. You published the paper already. So.
Yeah. So some of these variables we could get like as we did in the monthly model. Like for example, you could look at population, demographics, but because of this data is available at aggregated level. But then at the day level,
Yeah.
we cannot get that much of detailed data. And then like some variables like traffic that we will not be able to observe because just at a different kind of spatial level.
And your dependent variable looks, what is distribution look like?
I don't have a slide here, but it's a slight skewed, but not much skewed. Yeah, because like
It's somewhat
yeah,
normal.
it's not perfectly normal, but it's like yeah. But we tried different distribution with like with the long transform, but then this is the one that was the best performing model.
Other questions? No? All right. Well, let's give a hand to everyone.